Hello, class. Welcome to lecture 28. So today we're going to be talking about operations or binary operations. Um, and the idea is that we've already been using this word a lot, but now we want to make it precise. So we use the word operation, but as usual, you want to make things precise in math. And when you do that, it actually leads to a lot of very cool things. So intuitively, an operation, well, let's think about like operations we know about, like adding and multiplication. The real thing that they're doing is that they're taking two things and turning them into one thing of the same kind. So that's the intuition behind this definition. And I'm going to say the actual word, which is binary operation, but after this, I'm just going to keep saying operation instead. So keep that in mind. A binary operation or just operation is something which you sort of attach to a set. So addition is attached to some kind of number set. It could be the real numbers or the integers or something. So we say that an operation is on a set. So a binary operation or operation on a set A is, what it actually is it's a function. And functions have to go from and to something. So the idea is it goes from the product of the two sets, because then as an input of this function, you can plug in two things from that set. So if these were real numbers or something, then you could plug in two real numbers, and what comes out is one real number. So the function, it goes from two copies of the set to a single copy. And the name of the function, well, it just depends on the operation. So what we do right now is, because we're being very general, it's just like this little box. And so the box is your operation, and it takes your two elements to your single element that combines them. So typically what you do is you write this box in between the two elements to say that you're combining them with the operation. Okay. So an operation is really just a function that takes in two things and outputs one thing of the same kind. And then more fancy language, we say A is equipped. You'll see this kind of terminology a lot. Equipped with the operation. And then to sort of summarize the fact that you have a set and you have an operation equipped, or you have it equipped with an operation, you just sort of summarize it by writing something like this: A, comma, the operation in a little ordered pair. So this means, this tells the reader like, okay, I'm talking about a set A and it has this operation box. So it's just a sort of a summary. Okay, so let's see examples. Every time you see a new definition, you gotta have examples of it. And you have many examples in nature and in growing up. So plus is an operation on the integers. So using our fancy notation, plus goes from z cross z to z. So it takes in two integers and turns them into one integer like that. And this is an operation because the output is an integer still. So here's another one. Minus is another So you would write it like this. Takes integers in the inputs and turns them into m minus n. So plus and adding and subtracting are operations in this definition. However, if you change things ever so slightly, you break the definition. So for example, subtraction is not an operation if you only consider the natural numbers. Because if I take two natural numbers and I subtract them, this is not necessarily a natural number anymore. Because if I do like 3 minus 5, I get -2, which is not in the natural numbers. So it's an operation, but not on the natural numbers. On Z it is. Okay, so here's some more operations. Well, I'll just give you one more. Times is an operation, and it's a really good operation. It's an operation on the natural numbers, because if you multiply two natural numbers, you'll get a natural number. If it's an operation on integers for the same reason, for the rationals for the same reason, and the reals. So the basic premise is that when you multiply two things from the set, the result has to still be in the set. And that's true for all of these guys. If you start with two things in the set, the result is in the set. Okay, but those are boring because we've seen those operations a million times. So we got to get to something new. Otherwise, what's the point? So the first thing we're going to do is we're going to realize that operations are a type of mathematical gizmo. And every time we study a gizmo, we ask, like, can they have extra properties? And and operations can. So you've seen these before. For example, A times B is B times A. And so you say that times is commutative. That's the name of this rule. A times B times C, if I reorganize my parentheses, it's the same in either order. So then you say times is associative. Now it turns out the idea is that associativity is sort of more natural to do. It's a little bit easier for things to be associative. Commutative is actually a weirder property because you can sort of move things past each other, is the idea. Whereas associative things, you're not really moving things past each other. You're just changing what you do first. Okay, that's more thinky stuff. So let's do another example that has nothing to do with numbers. And now we can use this extra jargon. So given a set A, then union is an operation, but on what? On the power set of A. So remember what this is. This is the set of all subsets of A. So to be an operation on something, so it's an operation on this, means that it's got to be able to take, whoops, not the letters. It's got to be able to take two things from here, which is the power set. So that means it's got to go from that times itself and give you 1 as a result. And union does do that because union can take one subset of A and another subset of A. And if I take two subsets of A and I union them, it's still going to be a subset of A. So union is this operation that has nothing to do with numbers. And we've also seen that it's commutative. because I can union that way, or I could union this way and it's the same. And it's associative because if I union three things together, I'm just making one big old group of stuff. So it doesn't really matter if I do that. If I stick the first two together first, or I stick the second together first, either way, you just get a whole bunch of stuff. Okay, so that's another operation that has nothing to do with numbers, but you're going to say, you're full of it. That's still secretly about numbers because sets, we learned about finite sets and how all the cardinalities are just numbers. And so if you have a set with 10 elements, it might as well just be the set 1 through 10. They're all the same. Okay, fine, you caught me. So here's a more interesting one. So you got to stick with me here. It's going to be cool, but it's going to be maybe difficult. So here's a more interesting operation that this has nothing to do with numbers. So consider an equilateral triangle. Now don't get scared. You're not going to have to remember trig or geometry really. So an equilateral triangle, and I'm going to label the sides A, B, and C, or not the sides, the vertices, like that. So then what you should notice is if I rotate this triangle, so I'll do the calculations for you, 120 degrees, it just gives you the same triangle, except that the letters have moved. So I'm rotating this way. So the letters are now A is there, B is there, and C is there. And we want to think about this sort of as an operation. Well, actually, it is really an operation. We'll make it more precise later. It's an operation on the triangle, but that's a bit fancier to think about it. We're going to make it a little easier than that. And then I could do other things. So I could also rotate more. So I could rotate, if I rotate, I'll do it right here, by 240 instead in the same direction, then I get the same triangle labeled differently. Now the A is over here, the B is there, and the C is there. And then the other types of moves I can do to send my triangle to itself, but relabel it, is I can flip the triangle symmetrically, flip over a vertex or vertex. So the idea behind that is, so for example, here's A, and it's perfectly symmetrical. So I can flip over this line, and that's going to switch B and C. So if I do that, if I flip over the vertex A, then I also get another labeling of my triangle. Wait, that's the same one. Oops. A, C goes up there, and now B goes down here. So that's another thing you can do to this triangle. So you should try to think about all the things you could do, but I'll give them to you right now. So now we're going to use this idea to create a set. So create the set G whose elements are the moves that turn the triangle into itself but relabeled. So basically, whose elements are ways to relabel the triangle. So what are they? So G, what can we do? Well, we got a couple up here. I can rotate 120 degrees. I could rotate 240. And then if I rotate 360, I'm back where I started. So if I try to go to another one, what's after this? 480. That would just be the same as doing this. It wouldn't actually create a new labeling. So that's not going to be an element of the set. Similarly, this guy, you can also think about as rotating not at all 0 degrees, and that would be the same. So you could use either guy to represent that, but I'll use R360. What else can we do? Well, we can flip over a vertex. So I'll label that as F sub A. This means flip across A. I could also flip across B, and I could also flip across C. So there's going to be 6 things in this set. And I would leave it to you to actually do each one of these moves and see that you do get 6 different triangles. So these do correspond to 6 different labelings. Of this triangle. So you could go check that yourself. That's a lot of just grunt work. I have a PhD. I don't have to do that anymore. So you have to do that. Okay, so go check that. And what we're going to move on now in this video to is just the higher level stuff. So this is the set. What are we doing today? We're learning about operations. So I want to put an operation on this set. And that's the next step. So then we equip G with an operation. So remember, to equip a set with an operation, I've got to be able to take in 2 elements of the set and create a new element of the set. So how can I do that with these things? Well, what I can do is notice that no matter which thing I do, I still get a triangle. So if I do 2 in a row, I'll still get a triangle, which means doing 2 in a row will be like doing 1 of some other move. And that's the idea. So the way this will work is this will take in 2 elements of the set, and I just have to say in words what this operation is doing. So where this, means do X, then do Y. So for example, I could do R120, comma, FA. So this means I should rotate my triangle by 120 and then flip the triangle over A. So you'll notice this guy, for this to be an operation, what better happen? That better end up being one of these 6. Because when you do an operation, like if I do 5 plus 3, I don't create some new number that didn't exist already in the real numbers. It's just back in there. So this better be back in the set G. So let's figure out what it actually is. It's got to be one of those. So I can just do the operation to see. So first I rotate by 120. And then I flip over A. So that's that guy there. And I have to think now, what is that the same as doing? That's got to be the same as one of these. So I gotta sort of look at it as from here to here. How can I just go straight from there to there? What is that gonna be? It's kind of hard to see it, but notice that there's this C in the corner for both. And what's happening is that this B and this A have been swapped. So what element of the set is this? This is flipping over C. So this operation takes these two guys and turns them into flipping over C. And now we have this new funky operation, so we can ask questions about it, like, is this commutative? So numbers are boring because they're commutative. This is going to be more interesting because it's not commutative. So let's see an example by calculating something else. So let's calculate what happens when I do the same thing but backwards. So this time I'll flip over A, then I'll rotate by 120. Is that going to be the same as first rotating 120, then flipping A? I don't think so, but we should check. So now I start with my triangle, and I flip over A. So A stays there, and these two get flipped. Now I'll rotate by 120. Oh, and been meaning to read that book. There's a accidental plug. Okay, so now I'll rotate by 120. So A will go up here, C will go here, and B will go here. So what is this the same as? Well, now I gotta zoom out a little bit and think, how can I go straight from here to there? It's hard to see it. Let's see. Oh wait, shoot, is it the exact same? Flipped over A. Flipped over A correctly. AC. Crap, it's the same. Ah, okay. Whoops. What did I do wrong? Okay, let's try a different example to show it's not commutative. Whoops. So to be commutative, it always has to work. So maybe those two do obey that property. Apparently, unless I messed up. Yeah. So maybe those two do obey that property, but this is not supposed to be commutative, so it's not going to work sometimes. So let's try this one. Calculate. I can't remember the spell because I'm so flustered. All right, what happens if I flip over A and I flip over B versus flipping over B, then flipping over A? Ugh, this doesn't work. Okay. A, B, C. So I flip over A, and then I flip over B. So I get C, A, B. Okay, so that's flip A, then flip over B. Now let's do the other way. Flip over B, and then flip over A. Better be different, or I'm gonna be mad. Flip over A gives you C, B, A. Oh, thank God. Okay, it's different. Okay, so that means that this operation is not commutative. These are not the same. So let's figure out what they are. So doing flip A, then flip B is the same as what? So how can I go straight from there to there? I believe that's just rotating by 120. Yes, it is. So this guy is rotate by 120. If I want to go from here to there, flipping B, then flipping A, what is that the same as? Let's see, that's rotating 240. So yes, these two guys are different. Okay, good. So it's not commutative. But it is associative. But just due to time constraints, I'll let you reason to yourself why it's associative. Okay, so the next thing we want to do is notice some other interesting patterns. So about operations, and then we'll come back to this example. So notice sometimes when we have a set and operation together, there's a special element of A which does nothing. So I'll have to give you some examples to show you what this means by do nothing. So for example, the real numbers together with the operation plus, what's the special element that does nothing? It's 0. Which obeys the property. So the property that I mean when I say does nothing is that if I use the operation with that element on any other element, it just doesn't do anything. I stick with A. In fact, I could do it in either order. So this is what I mean by does nothing. R times also has a special element. But it's 1 this time. And it obeys the same property, but with its operation, which is times instead of plus. So if I do A times 1, that does nothing to it in either order, so it keeps it exactly the same. And then one more example, not related to numbers, that we looked at earlier. So if I take the power set of a set and I use union, well, what element of the power set, so it's got to be a subset, has the property that if I union it with a subset of A, it gets me S, it stays the same. Well, if I union, I think of it as adding stuff in. If I add the empty set, that's what does nothing. If I union with the empty set, I get S. So it's going to be that. So it has the element, this guy, obeying the same property, but for its operation, and it also works the other way too. Okay, so this do nothing element is a very special guy, and it has a fancy name. So let's use the fancy name definition. Given a set A equipped with an operation box that you don't know yet, this special element is called E. We say the element E is the identity element. That's the name. It's the identity element if, no matter what other thing you take in A, if I use the operation with E, it just doesn't change it in either order. So that's what a identity element does in a set with an operation. So it depends on both the set and the operation. So what about notation? So when you have all this stuff, to summarize, you write the set, the operation, and the identity. So what this means is that I have a set with an operation with an identity element for that operation. So this summarizes it, the information that you're working with. So let's think about the very cool set that we created earlier. So what is the identity element for that set G we created with the operation of doing one way to move the triangle followed by another way to move the triangle? In other words, what does nothing? Well, rotating by 360 does nothing. So it's a good candidate for the identity element, but technically we do have to actually check. So it is this though. So you can check that if you do a different guy, like flipping and then rotating by 360, it's just going to stay the same. And if you rotate by 360 first and then flip, sorry, I changed notation on you. Oops. If you do the other way, same thing. And then it also is the same for all elements of G. Okay, but in this lecture, we're not really going to be proving facts so much. I just want to show you a bunch of cool stuff. So we're going to keep moving along. So the point is that G, comma, this operation, comma, R360 exists. So we have a set with an operation with an identity element. Okay, now to move on, there's something that always sort of comes along for the ride with identity elements. Well, not always, but you usually hope they come along for the ride. And it's this. So now notice that sometimes, so let's keep this simpler number example in mind. So R plus 0. So the real numbers with addition and 0 is the identity element. So sometimes, like for this guy, each element has an undo pair, meaning a way to turn A, if you combine it with this undo, back into the identity. And for this guy, it's just negative A. But the point is its property that it obeys is that if I take my original number and I add, if I use the operation with this undo guy, it takes me back to the identity. So it like gets rid of A is the idea. And it also works in the reverse order. So sometimes this happens, sometimes it doesn't. What about for multiplication? Well, if I have a number, how do I multiply by something to take me back to the identity element of that operation, which is 1 in this case? Well, you might remember it's 1 over A. But with one little caveat, which is that this doesn't always work. And we need it to be a for all statement. So up here, it's true that every single number has a negative that if I add it to The original takes me to the identity. But here it's not true because most numbers do have a way to get back to being 1, except 0. So 0 does not have an undo element, which is kind of annoying. So there is no 1/0 that would make this work. Okay, so in fact, this guy does not have an undo element for all elements you start with, but this one does. Okay, so now let's define it with the real words instead of saying the word undo. So here it is. Given a set A with an operation with an identity, we say that an element A and A has an inverse, is the right way to say it, called, so people use this notation to mean the general inverse for this in general when you don't know a specific one you're talking about. And it's the inverse if what? If you combine it using the operation, then it takes you back to that identity in either order. So let's think about for our fancy friend G here. So for the set G consisting of all the ways to move the triangle and relabel it together with that operation that does one and then does the other, together with rotating by 360, which is the identity, what's the inverse of, say, I don't know, R120? In other words, if I do R120, so I rotate by 120. Oops, I messed up the start. If I start by doing R120, how do I undo that to get me back to R360 total? So this is much harder than for numbers, right? So for like numbers, how do I change A back to 0? I just add negative A. This one is a little bit harder, but not too hard. You can sort of play around with it. So the idea is I have to figure out R120 followed by what is the same as R360. And so you could just plug in elements of G and see if any of them work. But if you think a little bit harder, you'll see that the answer is just got to be 240 because rotating 120 and then rotating 240 adds up to 360. So in fact, that is the right answer. So the inverse of R120 is R240 and vice versa. What about the inverse of flipping? That one's actually a little bit easier. So let's say I flip over C. How do I get back to where I started? Well, if I just flip over C a second time, that'll just take me right back. So this is sort of a more interesting thing. Oops, sorry, 360. Why is it more interesting? Well, because what we're saying is we have an element who's its own inverse. Which is a bit weird because that doesn't happen in numbers very often. So for numbers, what's the inverse of 3, it's -3. It's not the same thing. The only time it's the same is for 0. 0 plus 0 is 0, so 0 is the inverse of 0 for addition. But for this set, it's true 3 times, actually, because it'll also be true for flipping over A. Oops, R360. And it'll also be true for flipping over B. So now we have 3 elements whose inverses are themselves. Whereas for numbers, you really just get the 1. So it's a lot different than numbers. And inverses don't even have to exist. So for example, if I go back to the power set example, so I look at a power set of A where I combine stuff together with union, and the empty set is the do nothing element. If I have an element of the power set, aka a subset of A, and I want to union something with it to get me the empty set, there's nothing there. There's nothing I can do. So in fact, you don't have to have inverses in the first place when you do this kind of stuff. There's no way to union something with S to go back to the empty set. Okay, now we're just going to summarize, and then that'll be it. To summarize some cool things that people do, I'm going to use very fancy words and stick everything together in a big definition. So here's the full big picture of what's going on here. So given a set A, equipped with an operation, we say the following. So the idea is that mathematicians study, very often they study sets together with operations. But they do so very generally, so maybe not like a specific set and a specific operation, just in general. So what we want to do is define something in more generality, more abstractly. So what we're going to say is that if you have a set A together with an operation, we're just going to name that a new type of thingy to study. So this is called a monoid. So these are the fanciest words we're going to see in this class. It's called a monoid if the operation is associative. So remember what that means. That means that you got to have A box, B box, C would have to be the same as A box, B box, C, regardless of your grouping choice. And 2, A has an identity element. I guess I shouldn't use numerics because I used 1 up there. I'll just use dashes. So then what you can say is you could call the whole thing the monoid. So what people do is they say, okay, this is the definition of a monoid. What are all the monoids? What are properties of monoids that come from just this tiny definition? And that's a whole thing you can study. For some reason, people don't tend to study monoids so much, so I have to tell you this other one, just because you'll see it later if you go on to take more math classes. So instead of a monoid, it's called a group. If, well, you get the same first 2 rules. but you also have an identity with inverses. So everybody has an inverse. For any A in A inverse exists. And A inverse exists. So then what people do here is they say, okay, this is the definition of a group. It's got to have a set. It's got to have an operation that's associated. It's got to have an identity, and it's got to have inverses for everything. And then they say, like, what are all the groups? Can I classify all the groups? And what are properties of groups that come out of just these first couple of properties that are the definition of the group? So they ask those types of questions. For us, we're not going to get that deep into that, so we're just going to say some examples as part of the summary. So the natural numbers with addition with 0 is a monoid because addition is associative and anything plus 0 doesn't change it. But it's not a group because there's no negatives in the natural numbers. But if you stick in negatives, then suddenly you get a group. And you could stick in more and it's still a group. So you could stick in rationals instead of reals and it would be the same. If you try to do multiplication, it gets a little bit more annoying because of 0. To be a group, every guy has to have an inverse, but 0 does not. So we cheat and we say, okay, fine, that's not a group. But if I take away 0, now this is a group because now every A has an inverse called 1 over A for multiplication. And then the guy that we just worked with, the triangle thing, that turns out to be a group too. So everybody does have an inverse. We have to go check each individual one. The power set 1, remember that one did not have inverses, but it did have the empty set as the identity element, so it is a monoid. The operation was associative. Another example, if you want to go figure it out real quick, I'm not going to do it in detail, is this. If I use intersection instead, still just a monoid, not a group. But now the identity element is the entire set A. Okay. Is that right? Off the top of my head now, I think that's wrong. So go figure it out on your own if you want. Okay, I don't want to claim that's right without thinking about it more. Okay, so then people do, like I said, is they classify things. So then the major goal of big branches of math is classify monoids or groups or whatever you want. And you could make more. These are called algebraic structures. You could make more by actually thinking about what happens if you have more than one operation at a time, and by adding in more properties. So you could say, well, what if the operation is also commutative? Then what happens? Stuff like that. So what we've done, so we actually classified finite sets. So what it means to classify is it means to say when are two the same? And we're able to do that. Or when are they the same up to renaming? When are they actually the same, but with different names? So for sets, that's what this was all about. And the idea was that two sets are actually the same up to just renaming things in the sets if they just have the same amount of things in them. But for groups and monoids, it's much harder because renaming things is not enough to tell you that they're the same because they have operations that have to also act the same. Okay, that's for much later. All right, so that's the end of today though. So see you next time.